essentially what we will be doing this week is reviewing the topics that we've seen so far in the class. So today we'll be doing a lot of old problems from some of the quizzes, some of the the midterms from last semester, just reviewing all those concepts just so that they stay fresh. What we'll do on Thursday is review some of the more recent topics, and then your final quiz 5, will be in a week from today in class. Okay, so how next week will work is it'll just be the quiz on Tuesday. So you come at 3:40, you do the quiz, and then you're done, free to go. And then on Thursday, we'll have a wrap-up lecture where we'll, again, summarize all the things that we've done, look at some other cool applications, and we can talk about things like course advice and what to do next. Does that sound okay? Cool. And also, homework 8, the final homework that everyone is required to do, is out now, and it's due on Sunday at 11:59 p.m., so that should be good preparation for quiz 5. And then there will also be the extra credit assignment, which will be for if you are just under the passing grade boundary, and that'll come out after quiz 5, and it'll be due towards the end of dead week, I would assume. Okay, but sometime during dead week it'll be due. Okay, but after quiz 5, after you do quiz 5 and have it all graded, essentially I'll just send you an email saying whether or not you need to do the extra credit assignment. So then there's no guesswork on your part. Okay, if you get the email saying you have to do it, you have to do it. Otherwise, you don't have to do it. Okay, and lastly, with regards to logistics, there will be a feedback form, sort of just for me to get your thoughts on how the course was run, and that'll be posted on Piazza by Thursday, and I'll probably give you a week to do it. Please fill it out once it comes out, and I'll post it again on Piazza, and I'll mention it, on Thursday, next Tuesday, and next Thursday. It sort of just helps us in, running the course. Okay, any questions? And it'll be anonymous. Okay, so let's get into it then. So, and we really won't talk too much about this today, but just a recap of what the binomial theorem states. It gives us a method to expand a binomial raised to some integer power, and we see that the coefficients are the elements in Pascal's triangle. Okay, and then we have this concept as a general term, but these are things that you'll review on the homework. Okay, so I won't talk too much about it. And then we also had Vieta's formulas, which allow us to interpret the sum and product and all these other relationships of the roots of a polynomial without having to find the roots themselves. We can do some tricks with the coefficients. And we also looked at a more general form of this. Any questions so far? Great. And so now let's bring it back to, January or February, and review all the things we sort of talked about. So the very first thing we talked about in the first or second lecture was the idea of a set. Okay, and we said a set is just a collection of mathematical objects, and then we looked at different properties of a set. So first it's cardinality, which for a finite set is just the number of elements in it. And we looked at set operations like the union of two sets, the intersection of two sets, the difference of two sets, the product of two sets. We looked at the idea of the principle of inclusion-exclusion, which gave us the cardinality of the union of two sets in terms of the individual cardinalities and the cardinality of the intersection. Right. Then we also rigorously defined all of these number sets that we've seen, out in the wild. So the set of, the naturals, whole numbers, integers, rationals, reals, and complex numbers. And we also compared each of these sets to see what their relative cardinalities were. Because remember, all of these sets are infinite, so we can't just say, okay, the cardinality of this set is 5, for example. Instead, we compared them and talked about whether or not each of these sets were countably infinite or uncountably infinite. And remember, all of these sets were countably infinite. And so these were countable. And the real numbers was the first set that we said, this is not countably infinite, so it's uncountably infinite. Then we introduced, somewhere, the order is not exactly right, but then we also introduced the idea of a function and how it really just takes one element. A function is just a specific type of subset of a Cartesian product of two sets, right? The Cartesian product of what's called the domain and the codomain. And it's a subset of that, such that there's exactly one element in this subset for every element of the domain, right? Because for it to be a function, it has to pass the vertical line test. So for any input, there's exactly one output. Not two outputs, not zero outputs, exactly one. Okay, and then we also talked about the difference between codomain and range. Codomain is the set of all possible outputs. Range is the set of all actual outputs. And then we also talked about propositional logic, so things like the conjunction, disjunction, negation, implications, A implies B, the contrapositive of that, not B implies not A, the converse of that, B implies A, so this is the contra positive, and this is the converse. And then we also looked at the idea of truth tables to prove the validity of different logical equivalences. Okay, so in the very first truth table we did was, prove that A implies B is equivalent to not A or B. Sound familiar? Sorry, excuse my cold. Then, after laying down those foundations, we moved into the idea of proof techniques. So the very first type of proof we looked at was a direct proof. Then we looked at different types of mechanics, like a proof by contradiction, where we start off by assuming the statement doesn't hold, and show that if we assume that it doesn't hold, it leads to some contradiction, which implies that the statement does hold. We had proofs by contraposition, where if we wanted to prove A implies B, we really just prove not B implies not A. And why do we do that? Well, because sometimes it's easier and they're logically equivalent. Okay, sometimes we also broke our proof up into different cases and handled them separately. And then, of course, we also talked about the idea of induction, okay, showing a base case, an induction hypothesis, and then showing that something holds, showing that the induction step holds. Meaning, if it holds true for the value of K, then it also holds true for the value of K plus 1. And again, we use induction when I prove something about all natural numbers. Prove statement about all natural numbers, or some subset of them. Okay? And then we also had a little lecture where we talked about series and sequences and proving different identities using induction and also deriving them using things like telescoping sums. Okay, and actually, there's a problem in the homework this week. I believe there's 5 questions. 4 of them involve binomial theorem or Vieta's formulas. And the last one is you sort of have to derive an identity on your own involving the triangular numbers, which it'll be similar to the stuff we talked about when we looked at series and sequences. So if you have any trouble with that, go and look. It was right before we started talking about number theory. So you can look at that lecture. Okay. Then we talked about number theory. So before even getting to modular arithmetic, we talked about quite a bit the idea that every integer can be expressed as a product of prime factors, things like the division algorithm, divisor times quotient plus remainder. Remember that. And then, of course, we talked about modular arithmetic, which we will review a little bit of today, and then the idea of how do we find an inverse, does the inverse even exist, those sorts of ideas. And I believe that's what was on quiz 3. Then a little more recently, after the break, we started talking about counting. So the idea of does order matter, does order not matter, permutations and combinations, right? Of course, we looked at the idea of n choose k. What does that mean? We looked at the special case of stars and bars. If I want to distribute 10 pieces of candy to 3 of my friends, how many ways can I do that? Just in general, how many ways can I do that such that everyone gets a single piece, such that one person gets exactly 3 pieces, one person gets at least 4 pieces, so on and so forth. Then we started looking at the properties of Pascal's triangle and explored this idea of combinatorial proofs, okay, which was on the last quiz, right? In combinatorial proofs, we wanted to prove that an equality holds not by doing some algebraic manipulation, but instead by arguing that the left-hand side and right-hand side of the equality count the same quantity, okay? And then more recently, in the last 2 weeks, we talked about the binomial theorem, of course, and Vieta's formulas. Okay, so that sort of summarizes all the things we've talked about in the semester so far. Any questions with a high-level overview? Okay, so basically the rest of today will just be us walking through problems from earlier in the semester. So again, you probably will want to have, pencil and paper out, and as we normally do, I'll give you a couple minutes to work on each problem, and then we'll take it up together. Sound good? Okay, so the first one is consider the mapping, which is just another name for a function, from the real numbers to the real numbers, given by, or the mapping that sends x to 5x cubed minus 2x squared plus 3. Is f an injection? Is it a surjection? And is it a bijection? Okay? So I'll give you a couple minutes. Try and remember what all of these things mean, and then we'll start talking about it. Okay? And I really want you to discuss with the people near you. Okay. So before we answer the question directly, let's review what these things mean. What does it mean for a function to be an injection? Yeah.
Doesn't that mean the domains, the number of cardinality of the domain is less than or equal to the cardinality of the
Well, that's like an equivalent condition, but what's the definition of an injection itself? Like, what is a function that is an injection? Sure.
Maybe if two inputs map to the same output, the inputs are the same.
Exactly. So an injection was the class of functions that no two inputs map to the same output. All right? And there are two equivalent ways of expressing this that said that if f of a and f of b were equal, that implies that a and b are equal. So that a and b are really the same thing. But another way to express this would be the contrapositive of this, right? Because that's logically equivalent. And the contrapositive might make a little more sense. We can say if a is not equal to b, that implies that f of a is not equal to f of b. Is that clear? Basically what this is saying is that no outputs are repeated. Is this okay? Cool. Yeah.
The equivalent statement still stands, right?
If that statement is true, then the function, then an injection exists, if that makes sense. But it doesn't make every function between them an injection.
Okay, because if the cardinality of the domain is less than the cardinality of the terms, doesn't there have to be?
Like you can make any function to be not an injection or not a surjection, right? But for there to exist an injection, it needs to be the case that the cardinality of the domain is less than or equal to the cardinality of the range. Of the codomain, sorry. Required for we're talking about injection, so injection to exist. Great. And now what was the definition of a surjection? Yeah.
The codomain has to be the same as the range.
Good. So one way to think about it is that the codomain has to be equal to the range. But what is the range? And what is the codomain? What's a little more rigorous way of putting this? Sure.
So the range is like every possible value that we're allowing, right? And then
That's the codomain.
that's the codomain.
Yeah.
So there's and then the range is like the actual.
Yeah. So the codomain is the set of all possible outputs, whereas the range is the set of all actual outputs. So a function is a surjection if and only if the codomain and range are the same set. Well, what we can say is that in both of these cases, assume that our function has domain A and codomain B. What we can say is for every element in the codomain, there's something mapping to it from the domain. And this was that formal definition we looked at. For everything in the codomain, there's something pointing to it from the domain. And the condition that we require for that to exist is the cardinality of A has to be greater than or equal to the cardinality of B. And if you want to think about this in terms of the circle diagrams, a function is a surjection only when every element in the codomain has an arrow pointing to it, right? Whereas an injection is one where no two things in the domain point to the same thing in the codomain. Okay, so this, for example, we can, I guess that's also a bijection, but this is an example of an injection. Okay, no two things in the input map to the same thing in the output. But for example, we could have something in the output that isn't mapped to. Is that clear? Okay, so now let's think about it in terms of the functions we're given. Okay, and a bijection is just both. Is this function an injection? How many people say yes? Okay, how many say no? Okay, well, why do you say yes?
It's an injection because, like, you know, like an injection is a one-to-one function.
Yeah.
So like every input has a unique output. And
Yeah.
one way you can test if it's one-to-one is use the horizontal line test.
Okay.
And you know, based on the shape of this quadratic, like it's going to like pass the horizontal line test.
Okay. Do you have a reason as to why you said no?
I thought it was possible it could not pass the horizontal line test because it has the square and the cube.
Yeah, so this is actually a cubic.
Yeah.
So it turns out that this is not an injection. And so the standard way you could do this would be to take the derivative and see if it's always non-negative, right? See if it's always 0 or positive, okay? To see if the function is increasing generally, right? Well, it'd have to be strictly increasing because you don't want to repeat any value, right? If the function is always increasing or always decreasing, then you will never repeat a value. So you could do that, and you could take the derivative, see that it's equal to, I think in this case, 15x squared minus 4x. We see that it factors, and that means there's some range where it goes less than 0. Okay? A little more straightforward way, though, is, this is going to seem kind of random, but we'll look at f of x and set it equal to 3. Okay, what do I get by setting it equal to 3? Well, that implies that I'm looking for some x such that 5x cubed, sorry, minus 2x is 0. That should be a 2x squared. But I can factor the left-hand side as x squared. 5x minus 2 is equal to 0. So this gives me that both x is 0 and x is 2/5 make the function equal to 3. But 0 and 2/5 are not equal. Is that clear? Right? So what this gives me, x is 0 and x is 2/5 both set f of x equal to 3, but 0 is, of course, not 2/5, therefore not an injection. Is that okay? So you see that the value of 3 is repeated as an output. But I will admit, so if you look at the plot of it, it's very misleading, and it's kind of hard to see at this scale, but like from just looking at this, it looks like an injection, but it's not, and it's because around here it actually goes up and then down and up again, but it's really hard to see that. Okay, I guess we could zoom in if we really wanted to, but I mean the math speaks for itself. It's not an injection. Okay? Any questions with why it's not an injection? Okay? Is it a surjection? Any ideas? is f a surjection? Yeah.
I think yes, because upper bound goes to positive infinity, the lower bound goes to negative infinity.
Yeah. And so it is a surjection. And we talked about this earlier in the course. If you have a polynomial of odd degree, one tail will always go to positive infinity and the other will go to negative infinity. That means any value you want in the real numbers will be hit somewhere. And that's not true of polynomials of even degree, because polynomials of even degree always have either a local maximum, a global maximum or global minimum, right? Which means anything above or below that won't be hit by the function. But polynomials of odd degree have neither a global maximum nor a global minimum. Okay, and you can infer from the plot, right? It'll go both towards positive infinity and negative infinity. So any value you want, you can find it hit somewhere here. Okay, and then is it a bijection? No, because it's not an injection. It has to be both to be a bijection. So because not injection. Great. Any questions with this problem? Okay, let's move on. Prove that there are no integer solutions to x squared minus 3 is equal to 4y. So this was a question on an earlier homework. We probably won't spend too much time on it, but it's just sort of to get you thinking about it again. So I'll give you a couple minutes to talk about it.
At least in X and Y issues.
Yeah. Should have mentioned that, sorry. Well, actually that's what you're trying to prove. You're trying to prove that if there are no two integers x and y that satisfy this.
Oh.
Yeah. Okay, so again, this has already been a question that you did directly, so I want to go through it pretty quickly because I think there are a couple more other interesting questions, but we'll do this by proof by contradiction. Okay, so we want to prove that there are no integer solutions to this expression, so our contradiction, so to do a proof by contradiction, you start by negating the original sentence, and so we'll assume that there are integer solutions. Okay, so assume x and y are integers satisfying x squared minus 3 is 4y. And so how can we proceed from here? So now we're assuming x and y are integers that satisfy this expression. Now what? Any ideas? How can we proceed from here? Yeah.
I'm not sure at all, but is it where you
Yeah. Yeah, so what we'll do is break up x into two cases, one where it's even or one where it's odd. And we know x will either be even or odd, so this enumerates all possible cases. So we'll look at case 1, where x is even, and case 2, where x is odd, and we'll show that in both cases there's some sort of contradiction. Okay? So in case 1, we'll assume x is even, so what we'll do is we'll say x is equal to 2 times k, where k is some integer. Is that clear? And if we assume it's odd, we'll say x is 2k plus 1, where k is some integer. Sound familiar? Hopefully. Okay. And so now let's plug in 2k for x. So we get 2k squared minus 3 is 4y. Then we have 4k squared minus 3 is 4y. And remember, we're looking for a contradiction. So what's the contradiction here? What is the contradiction? Yeah.
The left-hand side is odd because you're subtracting 3, but
Yeah.
the right-hand side is even because you're taking multiple 4s.
Exactly. So the contradiction here is that the left-hand side is supposed to be odd, right? Because 4k squared is even, 3 is odd, and the sum or difference of an even and odd is always odd. But the right-hand side is even. But you can never have an odd thing equal to an even thing, so therefore this is a contradiction. Is that clear? Okay, so we said that x is even, plugged in 2k for x, and showed that one side of the expression would be odd, one would be even. That doesn't really make any sense. Now let's look at the other case. 2k plus 1 squared minus 3 is equal to 4y. Then we have 4k squared plus 4k minus plus 1 minus 3 is 4y. Now where does the contradiction come from here? It's very similar, but if we do a little bit of simplification, here we have 4k squared plus 4k minus 2 is 4y. So now both the left-hand side and right-hand side are even, so we can't use the exact same logic. But how can we still find a contradiction? Where can we find a contradiction? Yeah. Yeah, both sides are supposed to be multiples of 4 because when you add a bunch of multiples of 4, the result should also be a multiple of 4. But if we want to see it a little more directly, we can just divide both sides by 2, and we get the exact same thing. But both are equivalent. So we can divide both sides by 2. And on the left-hand side, we have something that's odd, right? Because it's even plus even minus odd, so that's odd. And the right is even. And again, that's a contradiction. So we showed that in both cases, we arrive at a contradiction. Therefore, the original thing we assumed has to be true. Sorry, the original thing we assumed is false, so that means the negation of it is true. But the negation was the thing we were trying to prove. And so therefore, there are no integer solutions. Sounds good? Cool. Okay, now we'll bring it back to induction. So prove using induction that the sum, going from I is equals 0 to n, of 2 to the minus I is equal to 2 minus 2 to the exponent n. Okay? So this one's a relatively standard induction proof. It's sort of just to get you thinking about the mechanics of induction again. But I'll give you a couple minutes to talk about it and we'll get back together. There's a pretty significant typo in the way the question was worded, but it didn't really make sense the way it was worded. Okay, let's come back together. Okay, so so the typo was pretty significant. It wouldn't really make sense because the terms of the form 2 to the minus I, it gets smaller and smaller, but 2 to the n gets bigger and bigger. So that wouldn't really work. And so you could also do this by using the formula for the sum of a geometric sequence, where the first term is equal to 1, the common ratio is equal to 1/2, and the number of terms you actually have is n plus 1, because we're going from I is 0 to n plus 1. And so the formula for that, I think we talked about it way earlier in the course, would be a times 1 minus r to the number of terms over 1 minus r. But in our case, the number of terms is n plus 1 over 1 minus 1/2. And you could do the simplifying, and it would work out. Okay, you can see in the bottom you have 1/2, right? 1 minus 1/2 to the n plus 1. But if you have 1/2 on the bottom, it's the same as multiplying the numerator by 2. And it works out to 2 minus 2 to the minus n. So it works if you do it like that. Okay, but it should work. We want to do this using induction. Yeah. Because the n here is the number of terms. Yeah, and the sum starts at 0, so there's n plus 1 terms. But what we wanted to do is do this by induction. Okay, so what's our base case here? N is 0, great. So on our left-hand side, what do we have? Well, we have the sum of I going from 0 to 0 of 2 to the minus I. Well, that just looks like 2 to the minus 0, which is 1. We're good? On the right-hand side, we have 2 minus 2 to the minus 0, which is 2 minus 1, which is also 1. So base case, we're good. Our induction hypothesis will assume that the statement holds true for some arbitrary integer k. So we'll assume, the sum from I is equal to 0 to k of 2 to the minus I is 2 minus 2 to the minus k. Okay, and now let's look at our induction step. I'll clear this off just so we have more space. Yeah, we don't really need that. And then the induction step. Okay. Now we want to look at the sum going from I is equal to 0 to k plus 1 of 2 to the minus I. And we want to show that it's equal to the right-hand side of the expression if we were to plug in k plus 1. Right? So remember, we want to start from the left-hand side, work towards the right, or vice versa. Okay? But as you probably noticed, if we have a sum with indexes going from 0 to k plus 1, we can break it up into a sum going from 0 to k plus the term k plus 1. So I can say this is the sum going from I is 0 to k plus whatever the term is when I plug in k plus 1, which is 2 to the negative k plus 1. Then I can use the induction hypothesis here, right? Which should give me 2 minus 2 to the minus k, right? Is that clear so far? What's circled is essentially what we have in the induction hypothesis. And then I have plus 2 to the minus k plus 1. Okay, how can we combine those last two terms? Well, to make it a little easier to see, let's write them as fractions, okay? We have minus 1 over 2 to the k plus 1 over 2 to the k plus 1. Well, what can I do? I can multiply both the numerator and denominator of this first one by 2. And the denominators of both of them are the same. They're both 2 to the k plus 1. The numerator, I have minus 2 plus 1, which just gives me minus 1. So then I have 2 minus 1 over 2 to the k plus 1. Just by combining the last two terms using a common denominator. And then we're good. Because that's just 2 minus 2 to the minus k plus 1. And we're good. That's exactly what we wanted to show. Any questions with this? So this is another example of something that we can use another method to arrive at the result and then use induction to prove that the result actually holds. Okay, which I think we did quite a bit of in the course. Any questions? Great. This was another question that was on your homework that several people had questions about. The harmonic series h sub n is equal to 1 plus a half plus a third plus until 1 over n is known to be unbounded as n approaches infinity. Using induction, prove that for all n, the harmonic series up until 2 to the n is greater than or equal to 1 plus n over 2. And so part of it is doing that proof, and then the other part is interpreting why does this prove that the harmonic series diverges. Okay, so part one is just doing the mechanics of proving the statement that's given, and then part two is a little bit more of reasoning. Okay, so I'll give you a couple minutes to talk about this one, and then we'll come back together again.
Basically, that's it.
Yeah, it's like that. It's like, every number
Okay. So I've already started a little bit of the proof. So remember, every inductive proof has three components. One is establishing that the base case holds. In this case, the base case is when n is equal to 0. And we see that the left-hand side of the expression, when n is 0, is equal to 1. Right-hand side is equal to 1, and 1 is greater than or equal to 1. So we're good. Then our induction hypothesis, we're going to assume that this statement holds true for some arbitrary value of k. And our induction step is where the fun really happens. So what we want to do is look at h sub 2 to the k plus 1. And remember, we want to, in some way, use the induction hypothesis. Okay? So, any ideas on how we can proceed? How we can rewrite, how can we rewrite this sum, right? Because this is just a sum, to use our induction hypothesis. Any ideas? Okay, well, let's write out what the terms in the sum look like. Okay, whatever. H sub 2 to the k plus 1 looks like 1 plus a half plus blah, 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 plus 1 over 2 to the k plus 1 over 2 to the k plus 1. Notice how the plus 1 is not in the exponent, right? Plus 1 over 2 to the k plus 2 plus blah, 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 plus 1 over 2 to the k plus 1. Do you agree with this statement? Any questions with that? Okay. But this first part is just our induction, it's just h sub 2 to the k. So we can use our induction hypothesis somehow. Okay. And now, how can we combine these terms at the end? And remember, all we care about is an inequality. It doesn't have to be equal. Any ideas? Okay, so I guess here's my question. Oops. In this, well, okay, first let's establish. How many terms are in the sum that I've circled? How many terms are there? 2 to the k terms are in this first sum. And how many terms are in the second sum? Also 2 to the k. Because in total, there are 2 to the k plus 1 terms. Okay, and 2 to the k plus 2 to the k is equal to 2 to the k plus 1. In the sum that I've highlighted, what's the smallest term? The last term. Would you agree with that? Okay. And so the trick we will use is essentially using this logic. Okay, suppose we have 1 plus a half plus a third plus until 1/10. You agree the 1/10 is smaller than is the minimum value of each of the terms of the sum. Okay, so this is greater than or equal to the sum I would get if I just replaced everything with 1 over 10. Do you agree with that? Because 1 is less than 1 over 10, 2 is less than 1 over 10, and so on and so forth. It isn't necessarily meaningful, but it's true. Do you agree with this? Okay. So using that logic, I know that all of the terms in this highlighted part are all greater than or equal to this last thing, which is 1 over 2 to the exponent, k plus 1. Is that clear? And how many of those terms are there? 2 to the k. Right? And so I can say this is h. So now we're going to have the inequality. So greater than or equal to h sub 2 to the k plus 2 to the k terms of the form 1 over 2 to the k plus 1. And so this is exactly just replacing essentially the sum 1 plus a half plus until 1 over 10 with just all 1 over 10s. And replacing all the elements with the smallest value in the sum. Of course, the inequality will hold. And you can see that we can do a little bit of canceling, and the 2 to the k divided by 2 to the k plus 1 just becomes 1/2. Is that clear? And then using the induction hypothesis, we have another inequality, 1 plus k over 2, but now plus this half at the end, which gives us 1 plus k plus 1 over 2. And we're done. Okay, so we've shown that the harmonic series up until term 2 to the k plus 1 is greater than or equal to 1 plus k plus 1 over 2. Is that clear? So any questions with the process of this inductive proof? Okay? And so now, what about part 2? We won't spend too much time talking about it, but why does this prove that the harmonic series diverges? Yeah.
1 plus n over 2 diverges, and the harmonic series is greater than that.
Yeah, exactly. So let's just look at this sum over here. The thing on the right-hand side, like 1 plus n over 2 as n approaches infinity. This thing also approaches infinity, right? And the harmonic series is bigger than something that approaches infinity, so it also has to approach infinity. Okay, and then your question might be, well, we're looking at the harmonic series of up until term 2 to the n instead of just n, but it really doesn't change anything. Okay, essentially what this tells you is pick any large real number. I can find some, I can sum some number of harmonic series terms, and it will be bigger than that real number. Is that okay? So since 1 plus n over 2 diverges, the harmonic series also diverges. Any questions? Great. So now this one was also in the homework, and I'll zoom in a little. Prove that this statement holds true. Okay, so I'll give you a couple minutes. Okay. So, any ideas on how we can approach this? Any ideas? I mean, you could have just looked at the homework solution, but let's just assume you didn't do that. Okay, so this one's tricky, and there's no real formulaic technique to doing questions like this. You just sort of have to pick up the patterns. What we can do is encapsulate the relationship in this variable, or in this expression, by saying x is some variable such that it's equal to square root of 2 to itself. So x is defined recursively in this way. Is this okay? Any questions with this definition? Okay? And so now all we want to do is find the x that satisfies this. Okay? And so how can we do this? We can take the log of both sides and just assume we're talking about natural log, but it doesn't really matter. Is that clear? So I have log of x is x log square root of 2. But using my log rules, I know that square root of 2 is really 2 to the 1/2. So this is really 1/2 x log of 2. Is that clear? And I can do a little bit of rearranging, and I have log x over x is equal to log 2 over 2. So this gives us pretty directly that x is equal to 2. Is that clear? But, and I don't know if you looked at the homework solutions or not, is x is equal to 2 the only solution to this equation? Is x is equal to 2 the only solution? X is equal to 4 also satisfies it. Okay, just look at this original thing. You plug in 4 on the left-hand side you have 4. Right-hand side you have square root of 2 to the exponent 4, which is the same as 2 squared, which is the same as 4. So x is equal to 2 and x is equal to 4 both satisfy that. And so I know we're pretty sure that the value is 2, but how do we know that it's not equal to 4? Any ideas? How do we know that the true value isn't 4? So what we can do is we can prove that, so suppose we define a sequence that t of 0 is square root of 2 and t of n is equal to square root of 2 to the exponent t of n minus 1. You can prove that the terms are upper bounded by 2. Okay, so you can prove that t sub n is greater than or less than or equal to 2. And in fact, they get closer and closer to 2, so the true limit is equal to 2 and not 4. Okay, and we won't do that now just because I want to look at a couple other questions, but it's not that hard. If you do it with induction, you have your base case, right? You just look at t sub 0 is square root of 2, which last time I checked is less than or equal to 2, so that's fine. Your induction hypothesis, you really just state the statement again. And your induction step, it's not too bad. But I'll leave that as an exercise for you. Yeah?
Should we expect to see recursively defined variables more in the future in our math classes?
depends what math class, but yeah, it's not like anything too crazy. But at the same time, I wouldn't say they like look at this like regularly, if that makes sense. It's just something I think you should be aware of. Any questions? Cool. So here's another example to look at, but I'll also give you the attendance list at the same time. Okay, so I'll give you some time to fill out the attendance link and attempt the next question, and then we'll come back together and work on it. So it seems, how many people here are taking 70 over the summer? So I'll be the head TA for 70 over the summer, so we will see each other again. Can't escape me. Yeah.
I heard sometimes the classes are taught by just like by TAs. Is there professors for?
So like the summer CS classes are basically always taught by someone who was a GSI for it, or like the grad student of one of the profs that normally teaches it. So the people teaching it this summer, James, he's TA'd 70 and 170 several times. And Elizabeth, I think she is also TA'd, but I know she's one of Rao's grad students. But like those will be the like professors.
Okay.
Yeah, and so like no faculty member will really be involved, if that's your question. Okay, and remember, just we'll take up the question in another minute or two. Okay, so first let's start with the direct proof. Okay, and there's really several ways you can do both the direct and contraposition proof, but these are just two different ways. Okay, so if we're doing this directly, let's look at P, right? And we know that it's greater than or equal to 5, so it has to be odd. Is that clear? So that means both P plus 1 and p minus 1 are even. Is that clear? Also, since we looked at this earlier in the course, if you look at any 3 consecutive integers, one of them is a multiple of 3. Does this sound familiar? And we know it's not going to be p because p is prime. So that means either p plus 1 is a multiple of 3 or p minus 1 is a multiple of 3. Is that clear? Right? So in any 3 consecutive ints, 1 is a multiple of 3. And we know it's not going to be p, so it's either p plus 1 or p minus 1. So we have one case where p plus 1 is a multiple of 3. But we know both p plus 1 and p minus 1 are even, so that really tells us p plus 1 is a multiple of 6. So that gives us p plus 1 is equal to 6 times k for some integer, but that gives us p is 6k minus 1. So that's one case. And the other case is when p minus 1 is a multiple of 3. Well, again, that means p minus 1 is a multiple of 6, right? Because if a number is a multiple of 2 and a multiple of 3, it's a multiple of 6. So then we have p minus 1 is 6 times k, which gives us p is 6k plus 1. So we have that if p is some prime greater than or equal to 5, one of these two things hold. Sounds good? Great. How can we do this with contraposition? So remember what we want to prove is p is prime implies p is 6k plus 1 or p is 6k minus 1. How do we prove this using the contrapositive? What would the statement we'd be trying to prove be? Yeah.
You try to prove that if p is neither 6k plus 1 nor 6k minus 1, then p is not prime.
Exactly. It's kind of messy. Great. So now what we're going to show is that if p is not equal to 6k plus 1 or 6k minus 1, then it's not prime. Sounds good? Well, I said or. I should have said and. But okay. So if it's not 6k plus 1 and it's not 6k minus 1, do you agree that 6k minus 1 is really the same thing as 6k plus 5? Right? Since we're thinking modulo 6, even though we're not explicitly saying that. Then there's only 4 other cases to look at. P is 6k, 6k plus 2, 6k plus 3, or 6k plus 4. Is that clear? But what we see is that in each of these cases, we can show P is not prime. In the first case, when P is 6k, well, it's 6, it has a factor of 6, so it's not prime. In the second case, we can write this as 2 times 3k plus 1. It's even, and we know it has to be greater than or equal to 5, so it can't be prime. The third case, we can write this as 3 times 2k plus 1. It's a multiple of 3, so it's not prime. And in the last case, we can do the same, 3k plus 2 times 2, so that's also not prime. So in all 4 of these cases, we showed that we can write p as 2 times some other integer or 3 times some other integer. And since p has to be greater than or equal to 5, like for example, we can't set k to be 0 here because that would give us 3, but 3 is prime. But we're looking at primes that are greater than or equal to 5, so we don't really have to worry about that. Okay? And if our primes are greater than or equal to 5, k has to be greater than or equal to 1. So any questions with this problem? Cool. And so the last one we'll probably go through today, unless we have time for one more, is suppose n is an odd positive integer, and suppose that the function L of n gives you the last digit of n. Determine the last digit of this weird-looking quantity. So a big part of this question is identifying what is it really asking, like what does it mean in terms of things we already know, and there's also a nice little trick involved as well. Okay, let's come back together. So the first question is, in terms of things we already know, what does the last digit of n, like what does that really compute? Pardon? If it's odd? Not quite. You're close. Yeah. N mod 10. Yeah. Because the last digit is just the remainder you get when you divide the number by 10. So L of n is really just n mod 10. What does this sum mean? Well, it's just 1 to the n plus 2 to the n plus blah, 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 plus 10 to the n. This okay? Cool. And so now what we really want to compute, so L of this is just whatever this is in modulo 10. Is that clear? So let me write this out. 1, 2, 3, 4, 5. I'm going to write this an interesting way. 6, 7, 8, 9, and 10. Okay, same sum, I just wrote it in a funky order. So any ideas why I wrote it in this order? And remember, we just want mod 10. Why did I write the terms in this order? Well, we notice in mod 10, 9 is equivalent to -1, 8 is -2, 7 is -3, and 6 is -4. This is all mod 10. Is that clear? So what I can do, and remember we're just working mod 10, this is the same as 1 to the n plus 2 to the n, 3 to the n, 4 to the n, and 5 to the n, plus negative 1 to the n, plus negative 2 to the n, negative 3 to the n, negative 4, and then just tack on the 10 to the n out there. Was this okay? Yeah.
This is always just mod 10. Does n being like an odd positive integer have any effect on it?
What do you mean by effect? Like the fact.
Does n need to be an odd positive integer for like this to be true, basically?
Nothing we've done so far assumed that n is an odd positive integer. But what we're about to do will assume that. Okay? And the fact that the reason why we need n to be odd and odd really is because negative c to the n, if n is odd, you still have the negative term. Or if n is odd. But if n is even, it's just the same as c to the n. Right? So we need it to be odd so that we can rewrite these terms as 1 to the n minus 1 to the n, right? Plus 2 to the n minus 2 to the n. 3 to the n minus 3 to the n. 4 to the n's. And then plus 5 to the n plus 10 to the n. Those 4 terms go away. And now we're just left with the last digit of 5 to the n plus 10 to the n. Mod 10. Well, whatever that is, mod 10. But 10 to the n is always 0 in mod 10. And 5 to the n, well, any power of 5 will always end in a 5. So it's just equivalent to 5. Okay, so let's see. Equivalent to 5. So it doesn't matter what n is, as long as it's an odd positive integer. The last digit of this whole thing will be 5. Is this okay? So any questions with this? Okay, so I think that's all we have for today. On Thursday, we will go over some of the questions from quiz 4, and then review some of the more recent topics, and then that should put you in a good position for the quiz. Okay, just a reminder, homework 8 is out, and it's due on Sunday.